Hello everyone, the topic of this video is how mathematicians measure size. In this video, we will observe three different ways of measuring size. Number 1, cardinality, number 2, density, and number 3, measure theory. We begin with cardinality. What is cardinality? It is the number of elements in a set. In this video, we're going to look at two kinds of sets. One of them is finite. A set of 1, 2, and 3 is said to be finite and has a cardinality of 3. Two sets A and B are said to have the same cardinality if a bijection exists between them. Note that all finite sets are countable. Now we proceed to infinite sets. These can be both countable and uncountable, and their cardinality is infinite. An example of countable sets is that of all natural numbers on the number line. This set of natural numbers has an infinite cardinality. Another example of countable infinite sets is that of rational numbers. Question asked is why are rational numbers countable? It is because a bijection exists between integers and rationals. Moving on to uncountable sets, an example of such sets is that of all irrational numbers on a number line. Look at a limited part of the number line and you will find an infinite number of irrationals. None of these form a bijection with the integers, which ultimately means that they are uncountable. Now we will discuss density. There are two kinds of sets when it comes to density. Number 1 are the dense sets. A set is dense in a specific interval L if every open interval of L contains at least one element or point of that set. Now, let's talk about some examples of dense sets. A set of rational numbers is always dense. To understand better, we take our interval to be 5 on the number line. Any open interval of 5 that we now form will contain a rational number. This shows that rationals are dense sets. The next example that we now look at is a set of irrationals. They are also infinite over the number line, and any intervals formed on the number line will contain at least one element of the set of irrationals. This makes them dense. Another type of sets are the nowhere dense sets. If there are no open intervals in which the set is dense, it is said to be nowhere dense, meaning that an interval exists that contains no elements of the set. An example of a nowhere dense set is that of natural numbers on a number line, meaning open intervals on the number line exist with no elements of the natural number set in them. Now, let's briefly discuss integration. Conditions for a set to be integrable, taking the Riemann sum of that set should be possible. Continuous sets are integrable as their Reimann rectangles can be made. We can make two kinds of rectangles for a continuous set, upper and lower rectangles. Area of upper rectangles should be equal to the area of lower rectangles for us to calculate integration. Discontinuous sets are also integrable since making its Riemann rectangles or squares is possible. We simply take the areas of all the rectangles and add these to get integration. Let's look at discontinuous sets that are not integrable. Example of a non-integrable set would be a set represented by f of x equals 1 if x is subset of rationals, 0 if x is subset of rationals complement. For this function, we have an infinite number of points when y equals 1 and y equals 0. Such a set is not integrable. This function is non-integrable because it is discontinuous over a dense set. In order to overcome difficulties pertaining to integration, mathematicians derive the idea of Lebesgue measure. Definition of this measure is that given a bounded set, S is a subset of A and B. Let C be the collection of all countable covers of S. The measure S is the infimum over C is a subset of C of the sum of lengths of the pairwise disjoint open intervals that constitute C. Measure of S equals infimum measure of E when C is a subset of C. Now, I know it is a complicated definition, but what is essential for us to know is that we can find a pairwise sequence of intervals which cover our set. The measure of our set is the sum of the lengths of the covering intervals. We will now determine the integral of f of x. This would be 1 into measure of rationals plus 0 into measure of rationals complement, which goes to 0, and we are left with measure of rationals. But What is the measure of rationals? For us to determine measure of rationals, we must cover the rationals in 0, 1 with pairwise disjoint sets. Since the rationals are countable, we can develop a scheme of covering them with countable intervals. All we have to show then is that these intervals can be made into pairwise disjoint sets. And finally, we have to measure and sum their lengths. We start by covering the rationals R1, R2, R3 and so on in the following way. What we do is assign intervals to each rational, naming them epsilon 1, 2 and 3. On the number line, the intervals will overlap. So we let epsilon I equals epsilon over 2I, then the sum of lengths would be summation I equals 1 to infinity epsilon over 2I, which would equal to epsilon into summation I equals 1 to infinity 1 over 2I, which would then lead to epsilon into 1 over 1 minus 2, and that would eventually give us 2 epsilon. But since the intervals are overlapping and have to be made pairwise disjoint, and since epsilon can be an arbitrary number, pairwise disjointness can happen if epsilon goes to 0, which will ultimately give us our answer. That is, measure of rationals equals 0. So, conclusively, the integral of f of x equals 0, and interestingly, measure of rationals complement equals 1 minus measure of rationals, which ultimately gives us 1. So, this video basically was a simplified version of how mathematicians measure sizes. Hope you enjoyed watching. The end.